Alright, so in this video we're going to talk about the graphs of inverse trigonometric functions. And just to go ahead and put your mind at ease, this won't be like the last video that we did where we actually had to graph these things in details. The purpose of this video ultimately is just to get some kind of familiarity with what these graphs look like and how they're defined. So we're going to start by giving you the inverse sine function, and then we'll introduce this by graphing the entire sine function. Now, one thing that we notice automatically about the sine function is that it's not a one-to-one function, meaning it does not pass the horizontal line test. I see, namely by the x-axis, that this function crosses that horizontal line at infinitely many places. So it's not a one-to-one function, but we can still carve out an analog, so to speak, of an inverse that does end up being pretty useful. So we need a function to be one-to-one in order for it to be invertible. So I'm going to graph the sine function on the restricted domain of negative pi over 2 to pi over 2, because this slice of the function is one-to-one. In other words, no horizontal line is going to cross this function more than one time. We don't go into too much depth when it comes to the inverse of functions, so we'll go ahead and tell you that if I want to get the inverse of a function's graph, then I have to plot the line y equals x and rotate that function 180 degrees about that line. So when we plot the function y equals x and we get this nice diagonal line and we rotate it about that line, we end up with the following graph. This is going to be the inverse sine function or the arc sine function. These two notations mean the exact same thing, but you can sometimes see it show up on calculators as either sine with a power of -1, which is notation for inverse, or arcsine. It's most common that you're going to see the arcsine notation in a programming setting. Softwares like Mathematica or languages like Python prefer the function arcsine to actually call on the inverse sine function. So because I have sliced off a huge portion of my sine function to flip it and get the arcsine function, I no longer have something that's periodic or goes infinitely in one direction or another. In fact, this function is neatly contained between -1 and 1. The rest of this video goes on to show you the graphs of the other 5 inverse trig functions, and then ends with some information about domain and range and some unit circle stuff. But we have 2 more videos in this section to talk namely about computational kinds of problems and the actual usefulness of inverse trig functions. But like I said, right now, this video we can kind of take it easy by just looking at some graphs and getting a feel for what each one of these looks like, and mostly how they're defined. By similar approach, we'll go ahead and look at the cosine function, which is also not one-to-one. But this time we're going to plot it on the interval from 0 to pi because this slice actually makes it one-to-one. We are still going to draw that diagonal line, y equals x, and rotate or flip our graph about that line. And this is going to give us the following graph for the cosine inverse function or the arc cosine function. So every one of our inverse trig functions abides by the same kind of notation. I either have something like cosine to a power of -1, which again denotes an inverse, or arc cosine. And each trig function is going to do the same thing, again for notational ease or for programming purposes. Next we'll talk about the tangent graph. I encourage you to look at the tangent graph on a graphing calculator like Desmos, but here we're going to graph it again on a restricted interval from -pi over 2 to pi over 2 so I can get one slice of it that's guaranteed to be one-to-one. Also a reminder that the tangent function is defined as sine divided by cosine of x. Now, we saw in the last video that the cosine function has -pi over 2 and pi over 2 as an x-intercept, meaning it's going to be equal to 0 at those values. So my tangent function won't be defined there because, similar to the idea of rational functions, I have a 0 denominator which gives me a vertical asymptote. So this is what one slice of my tangent function is going to look like. And when I flip it about that diagonal line, I now have a function that goes infinitely to the left or to the right, but it has an upper bound of pi over 2 and a lower bound of -pi over 2. So remember, we're looking at this graph of the tangent function on a restricted domain. The actual tangent graph repeats this same cycle shape infinitely many times to the left and to the right. And if you type it in on a graphing calculator, you'll see that happen. But here again, we're just graphing it on one restricted interval and flipping it to get our inverse tangent function. In a similar spirit, let's look at the cotangent function, which is defined as cosine divided by sine, and we're going to plot that on the same restricted domain of -pi over 2 to pi over 2. Now since negative pi over 2 and pi over 2 are x-intercepts for the cosine function, we know that the cotangent function is going to be 0 at these values, because that's giving me a 0 numerator. However, we also know that the sine of 0 is equal to 0. So I'm going to have a vertical asymptote at x equals to 0, which is going to give me a graph that looks like the following. Or, as I keep saying, this is only one slice of the cotangent function. You're again encouraged to check out its graph on a calculator. And finally, we're going to flip this on that diagonal line, and we're going to get the resulting graph. So something subtle happens here. I am filling in one circle at the point pi over 2, and I have an open circle at the point negative pi over 2. This is because if both circles were filled in, I would fail the vertical line test and no longer be a function. So I have to plug that puncture at one place and leave it open in another place. Next, we'll take a look at the inverse cosecant and the inverse secant function. Cosecant is defined as 1 over sine, so here on the dotted line we have the sine graph. And you'll notice if you look at the cosecant graph on a calculator, it kind of does the opposite of the sine graph because you have this reciprocal shape. So we'll sketch one slice of that here, and then again flip it on that diagonal line to get the cosecant inverse function or the arc cosecant function. And finally, we'll play a similar game with the secant function. We'll give you one slice of the secant function in a similar way, and then we'll flip it to give you the inverse secant function or the arc cosecant function. Now, are you supposed to walk away from this video having all these graphs memorized? No, of course not. We did a lot of this pretty quickly, and we stepped over quite a few non-trivial steps. The whole point again is just to see these graphs and get some familiarity with them, but we're not working with them to the same degree that we did in section 7.4. Now, the observant viewer will have noticed that the majority of our functions have been plotted on the restricted interval from negative pi over 2 to pi over 2, except for the cosine and the secant function, which get plotted on the restricted domain 0 to pi. So these two stand out a little bit, and we'll talk about why in the next slide. Here in this slide, we're just cataloging a whole bunch of characteristics about all these functions: domain, range, and an important topic for next video, the quadrants of output. Now here, we're referring to the quadrants of the unit circle. We're going to see in the next video how to use the unit circle almost in reverse order to help us with these inverse trig functions. Because at the end of the day, what does a trig function do? You input an angle and then you output some real number. An inverse trig function works backwards. You input some real number and then you output an angle. The notion of an inverse is that you have a function that's kind of working backwards. And as we work backwards, we have to be a little bit careful about what sections of the unit circle actually are relevant and which ones aren't. Remember, each one of these graphs was graphed on a restricted domain of the real line, which means that it's not covering the entire unit circle. In fact, each one of these inverse trig functions only occupies 2 out of 4 quadrants on the unit circle. Anyway, that's going to be the topic for our next video. Thank you so much for watching, and again, don't look at this video in an overwhelming way thinking that you have to memorize all this. You definitely don't. I'll say just one more time for assurance, this is just to build some familiarity.